Hello, my name is Mihai Dușmanu and I'll present an approach for cross-descriptor visual localization and mapping. This is a joint work between ETH Zurich and Microsoft. Mixed reality and robotics blend the physical and digital worlds to unlock the next evolution in human, machine, and environment interaction. This promise mostly relies on the technical capability to build and localize against maps of the environment. For example, collaborative experiences require co-localization of multiple devices into the same coordinate space. Similarly, relocalization against existing maps enables persistence and retrieval of digital content attached to the real world. In existing industrial or academic setups, a fixed local feature extraction algorithm is used throughout the evolution of a map. When a better algorithm becomes available, the process is repeated from scratch by extracting the new features and running matching followed by mapping. However, in practice, images are typically not shared across devices or uploaded to the cloud. This is primarily due to privacy reasons, but also to reduce bandwidth and storage requirements. Thus, it is impossible to re-extract features whenever a different representation is required. This introduces several fundamental limitations. First, existing systems cannot adopt new feature algorithms unless specifically designed for backwards compatibility. Second, co-localization and cross-source mapping scenarios with devices using different feature algorithms is impossible. This might be due to different software versions, different compute capabilities, hardware implementations, or different manufacturers. This incompatibility between feature algorithms severely hinders the essential step of feature matching required by most localization and mapping pipelines. As our first contribution, we identify, introduce, and formalize three novel scenarios for localization and mapping in a world of changing local feature representations. First, given a sparse 3D map, associated local feature descriptors, and no access to the original image data, the goal is to develop a mechanism enabling the continuous deployment of new feature representations. For instance, it should be possible to switch from handcrafted to learned descriptors, SIF to SOSNet, change their dimensionality, or update the model weights by using different training data, loss, or architecture. The scenario avoids an explicit remapping phase, which is generally very expensive and time-consuming. The previous scenario assumes the same feature extraction algorithm is running on all client devices. However, this is generally not the case, as legacy devices often cannot be updated due to hardware limitations. Thus, a mechanism for backwards compatibility is required to match across different device versions. Similarly, specialized devices such as headsets, autonomous cars, or mapping platforms could take advantage of additional onboard compute for a better localization performance compared to devices such as mobile phones or lightweight drones. It would be beneficial to co-localize these devices inside the same maps to avoid a fragmented scene representation. Finally, we consider multiple heterogeneous devices collaboratively mapping the same environment. For the aforementioned reasons, it is fairly unlikely for all devices to use the same features as in a standard academic setup, even when produced by a single vendor. Consequently, we end up with each device providing different types of features from which we need to build a single coherent map. To better understand our approach, we start by formalizing several notions. A feature description algorithm A defines a handcrafted or learned function mapping images to vectors in a high-dimensional space. In the case of local image descriptors, the domain is the set of patches normalized based on the estimated feature geometry, position, scale, orientation, or a fine shape. A perfect translation between two algorithms A1, A2 maps a feature vector of A1 onto the manifold of A2 such that descriptors extracted from the same input patch correspond. Our experiments empirically demonstrate that using multi-layer perceptrons to approximate the translation functions enables cross-descriptor matching for downstream applications. Given a pair of different description algorithms AI, AJ, one could approximate the translation function by a multi-layer perceptron Ni2j. To this end, we define the translation loss as the L2 prediction error for floating point descriptors. If the target algorithm produces binary descriptors, the regression loss is replaced by a classification loss. Training descriptors are simply computed by applying different description algorithms on a given patch to obtain a set of corresponding descriptors. To compute the distance between two descriptors di dj, extracted using algorithms AI, AJ respectively, one can translate from I to j by using the associated MLP, or conversely from j to I. However, it is not obvious how to use this approach in the collaborative mapping scenario, as there is a quadratic number of possible translation directions. One could use a progressive strategy that translates the weaker to the better descriptor for each image pair, but deciding which descriptor is more suitable is not straightforward. To address this issue, we turn our attention towards autoencoders. Each description algorithm AI now has an associated encoder EI and decoder DI, ideally satisfying DI round EI equals identity. To obtain a mapping from AI to AJ, one can change the encoder I and the decoder J. Furthermore, we use a triplet margin loss with in-batch hard negative mining to facilitate direct matching in the joint embedding space. Let us consider the embedding of a reference patch P using the encoder I. We then map all patches in the batch to the joint space using encoder J. The positive pair is simply the embedding of P using encoder J. The negative pair is the closest non-matching embedding using encoder J. In this case, to compute the distance between two descriptors DI-DJ extracted using different algorithms AI-AJ, one can map both to the joint space. Let us now move on to the evaluation of cross-descriptor visual localization. First scenario is continuous deployment. Given a set of database images, algorithm 1 is used to extract descriptors. Next comes feature matching followed by construction of a database model. Given a query image using algorithm 2 for description, one cannot directly match between query and database. In this scenario, the database descriptors are translated to the query ones, making matching and localization possible. Throughout this section, we consider two handcrafted descriptors, binary brief and histogram-based SIFT, as well as two state-of-the-art learned descriptors, HardNet and SOSNet. We notice an uptick in performance when migrating maps from handcrafted descriptors to learned ones. Furthermore, when localizing state-of-the-art descriptors against each other, the performance remains very close to the best performing one. Next, we consider cross-device localization. The setup is similar to the previous scenario, but instead query descriptors are translated to database 1. This, in turn, allows matching and localization once again. The conclusions are the same as with the previous experiment on continuous deployment. Finally, we consider the case of localizing to collaborative maps. In this scenario, the set of database images is split into n subsets, each using a different feature description algorithm. All database descriptors are mapped to the joint embedding for matching before mapping. The query image descriptors are also translated to the joint embedding space, followed by matching to database and localization. Although the map is built from heterogeneous descriptors, the localization performance at day is comparable to the best results during the previous experiments, notably when using learned descriptors. This is a very encouraging result for cloud-based solution as we enable multiple devices implementing different algorithms to not only collaborate on mapping a location, but also remain competitive with the state-of-the-art in localization. Next, we move on to the collaborative mapping evaluation. As before, the images of each dataset are split into 4 balanced subsets, one for each algorithm. We first consider the standard setup where one has access to the same feature descriptor for all dataset images. These baselines are not able to tackle collaborative mapping with heterogeneous descriptors, but they serve as an upper bound for our method. Next, we consider the real-world setup in which 4 types of devices with incompatible descriptors map the same environment, but the mapping system cannot jointly leverage them. Both our methods using either the joint embedding or a progressive approach drastically outperform these real-world baselines. Furthermore, despite only half the images having HardNet or SOSNet features, our approach outperforms standard maps built from handcrafted descriptors, but achieves slightly inferior results than state-of-the-art ones. We also provide visibility statistics of the 3D points for the model taking advantage of the joint embedding. An overwhelming majority of 3D points have at least 2 different description algorithms in their tracks, and more than 50% have 3 or 4. Furthermore, the co-occurrence matrix on the right demonstrates that all descriptors contributed almost equally to the final map. As can be seen, the real-world independent models using only a quarter of input images are quite sparse and incomplete. By jointly leveraging the different descriptors and establishing cross-descriptor matches, we can obtain a more complete and accurate model. In the supplementary material, we show additional results on several other datasets that confirm the findings presented above. Furthermore, we realize an extensive ablation study which empirically validates our design choices. The main limitation of our work comes from the same key point assumption, as we only consider the compatibility of different description algorithms. While our assumption is likely applicable for devices produced by a single manufacturer that has control over the entire pipeline, different manufacturers likely use different key point detection algorithms. Possible directions for future research include studying cross-detector repeatability or improving feature inversion techniques for better generalization. Furthermore, while we have made significant progress towards enabling cross-descriptor localization in mapping, several challenges still remain. First, each description algorithm only encodes a subset of the information available in the input patches, and these subsets might be distinct for different methods. Second, a one-to-one mapping may not even exist, as two given patches might lead to a similar descriptor for one algorithm but completely different feature vectors for another one. To address these limitations, future research could try to take advantage of local or global context to better disambiguate the visual information. You can join us during Poster Session 5 if you want to learn more or discuss our work. Thank you for your attention.